This presentation will explore the fundamental concepts of multi-threading in embedded C, highlighting how it enhances efficiency and responsiveness in embedded systems. We'll discuss key steps involved in implementing and managing multi-threaded applications within the constraints of resource-limited embedded environments. The RTOS acts as the foundation for multi-threading, providing essential functions like thread management, synchronization, and communication. It's crucial to choose an RTOS with features tailored to the specific requirements of your embedded application. Ensure that your chosen RTOS is compatible with your target hardware platform. Consider factors such as processor architecture, memory size, and peripheral interfaces. Compatibility is critical for seamless integration and proper functionality. Creating and managing threads. Thread creation. Use the RTOS API to create threads, assigning each thread its own stack space and execution context. The RTOS manages the memory and resources allocated to each thread. Thread execution. The RTOS scheduler dictates the order and timing of thread execution based on their priorities and scheduling policies. Each thread receives a specified time slice or executes until it blocks or yields control. Thread priorities. Assigning appropriate priorities to threads based on their criticality and timing requirements is crucial. Higher priority threads can preempt lower priority threads, ensuring time-critical tasks are executed promptly. Resource management. Memory management. Ensure proper memory allocation and deallocation for threads to prevent memory leaks or buffer overflows, ensuring efficient resource utilization. Peripheral management. Coordinate access to peripherals by multiple threads to avoid conflicts, ensuring proper functioning and data integrity of shared hardware components. Communication management. Manage access to communication interfaces, ensuring efficient data transfer and preventing conflicts between threads, guaranteeing reliable communication between different parts of the system. Error handling and debugging. Implement mechanisms to detect stack overflow conditions, which occur when a thread exceeds its allocated stack space, ensuring stability and preventing system crashes. Use error handling mechanisms to alert the system when an error occurs, providing valuable information for debugging and recovery. Implement strategies to recover from errors gracefully, minimizing disruptions and ensuring system resilience in the face of unexpected events. Testing and validation are crucial steps in the development process. We need to ensure that our multi-threaded application performs reliably under various conditions. This includes stress testing, functional testing, and code reviews. By thoroughly validating our work, we can catch potential issues early and improve the overall quality of our embedded systems. Remember, a well-tested application is key to a successful deployment. Unit testing. Test individual functions and components of the multi-threaded application to ensure they work as expected and meet the specified requirements. Integration testing. Verify the interactions between different components and threads to ensure seamless integration and proper communication between them. System testing. Validate the complete multi-threaded application on the target hardware to confirm overall performance, reliability, and adherence to functional and non-functional requirements. Conclusion. Multi-threading in embedded C offers numerous benefits, enabling developers to create efficient, responsive, and feature-rich embedded systems. The key lies in choosing the right RTOS, effectively managing threads, and using proper synchronization and communication techniques. By understanding these principles, developers can harness the power of multi-threading to create innovative and robust embedded solutions.